Hey guys, so in this video I'm just gonna quickly go through the 2018 electrical systems paper for level 3. So yeah, let's get to it. Um, Casey sets up a battery, a switch, and a 3 ohm light bulb in series. Explain why the battery voltage is less when the switch is closed, and that was when the switch is open. So this is gonna be our EMF. Uh, and that's going to be our terminal voltage or the voltage available to the circuit. Okay, and that's just going to be our R. Um, okay. Explain why the battery voltage is less when the switch is closed. So basically, when the switch is closed, right? So just putting this into so when the switch is closed, when the switch is closed, then current is drawn. And just like a quick, brief summary, you shouldn't actually write your answer like this. This is just a bit of a guide. But when the switch is closed, basically current is drawn, right? So um, is drawn. So the internal, I'll just write IR. The internal resistance increases. And just putting that into equations, right? Your voltage terminal is your EMF, um, minus your internal resistance, and this component here has like more current is being drawn from the circuit, therefore VT must decrease while I has increased, right? So basically that's why. And also you should note that when this switch is closed, open, sorry, then basically the resistance in this gap is nearly infinity. So no current will be drawn. So that way you will just be getting the raw voltage of the battery, which is your EMF. Okay, so we knew that, okay, Kc measures the current through the circuit to be 1.89 amps. State the EMF, so our EMF is 6.02 volts. And, okay, so we know that our voltage to the circuit um, is just your EMF minus your internal resistance, and so your internal resistance is just your EMF minus your voltage, and your resistance is EMF minus voltage on current, which is just going to be 5.85 and 6.02. So 6.02 minus 5.85 divided by 1.89, which gives me um divided by 1.89, and I get like 0.0899 ohms, which is 0.09 ohms to three significant figures. Okay, let's move on to the next one. Okay, so now it's a capacitor in series and closes the switch. Okay, as it charges. So capacitor voltage and our time. Okay. Oh, okay. So looking at our formula sheets, we know that our time constant is our resistance multiplied by your capacitance. So your capacitance is going to be your time constant divided by resistance. We don't really have our time constant, but time constant is the amount it takes to reach 63% of its maximum value. So if we take 63%, if I take 63.63 off maximum voltage, which was 6.2 or 6.02, I get a value of uh, 6.02. I get 3.79 volts. And 3.79, wait, 2, 4, 6, 8 is somewhere like right around here, which on the X is going to be exactly almost. So our time constant is going to be 1 times 10 to the minus 5 seconds. So if we just go 1 times 10 to the minus 5 divided by our resistance, which is right 0.09, and yeah, um, so that would just be 3.09 because that's our total resistance. So I should just write R total 3.09, which putting that in my calculator uh, gives me I get like 3.236 times 10 to the minus 6 farads, which is basically just 3.24 times 10 to the minus 6 farads to three significant figures. Okay, Casey discharges the capacitor, removing the light bulb, and begins to charge the capacitor again. Casey predicts that by removing the light bulb, less energy will be converted to light and heat, and so the capacitor will charge more quickly and have more stored energy once charged. Okay. So our time constant is your total resistance times your capacitance, and basically in bullet point form, don't actually do your answer like this, but since our total resistance decreases, that means that our time constant must also proportionally uh, decrease, um, and that just means that it takes less time to reach 63%, right? Of its maximum value. Okay, so yes, it will charge faster. So it charges, oh god, it charges faster, right? And with less energy, um, so because your voltage is going to be your current times your total resistance, and basically if your total resistance decreases, then your current must increase, and we also know that P equals I squared R. So although no energy lost to light, more is gonna be lost to heat, right? So even though none, like very little amount of that energy are like lost to light, more of it is gonna be lost to heat because there's a much larger current. More will be lost to heat. So it's kind of gonna be the same amount, same. Okay, and whether more energy will be stored in the fully charged capacitor. So the we know that by like if we go back to our default equation, we know that E equals half QV, right? So energy stored, E stored, is always 1/2 of what is supplied. And in this case, because our voltage is constant, so our supplied energy, which is constant, so supplied is constant, right? And so, no, the same amount of energy will be stored um, by the fully charged capacitor. So, yeah, let's move on to the next one. Casey is using an electromagnet that has an inductance of this and a resistance. Internal, okay. So we just know that our voltage is your current times your total resistance, and your current is just going to be voltage divided by your total resistance, and that's just going to be 12 divided by 2 plus 0.09, which, putting that in my calculator, I get 5.74 amps. Okay. Casey opens a switch and a large spark jumps across the terminals of the open switch. Okay, so basically, when the switch is opened, so when the switch um, is opened, when the switch is opened, right, then the current collapses from I max to 0. This means that your change in current over time is going to be less than 0, right? And basically we also know that, looking at our equations, where is it? Is there anything else of use? Not really. It's mostly thinking about these two. But oh yeah, and basically, as the current is changing, right? So basically, we can say, we know from the two equations, EMF equals negative d phi on dt, and also EMF equals negative L times di by dt. And if we set these two equal, then we'll get d phi by dt is equal to L times di by dt. And so we can just cancel these out. So we just get d phi is equal to L di. And so what this is just saying is that a changing current corresponds to a changing flux. So this changing I'm just gonna write to save my wrist. This changing I produces a changing flux. Um, and basically, if we go back to the equation, E equals negative L times di by dt, and note that di by dt is less than 0, so the two negatives will cancel out, and this will just become a positive EMF, which is L times di by dt, and because the whole purpose of the negative is for direction, right? So now the EMF acts in the same direction as the collapsing current. So EMF acts in the same direction as the collapsing current, and basically that just gives the current a boost. Sorry, it gives so it gives it a boost, which creates this massive spark across the switch. And we should also write that the EMF can be greater than whatever voltage is supplied, because Kirchhoff's voltage law does not apply, right? Because it's not a closed circuit once the switch is opened. So let's move on to the next one, because I think we've got that one done. Okay, to prevent damaging sparks, Casey places a on resistor and parallel with the electromagnet. Okay, so this is a Kirchhoff's question. Um, at one point, uh, okay, so 2 amps are drawn from the battery, and an EMF of 9 volts has been induced. Show that the current, okay, is 1.41 amps. Okay, so we're gonna have a 12 volt DC going this direction, right? So we're gonna have a total of 12 volts, right? And okay, I'm gonna analyze this full loop here, right? So not individually loop 1 and loop 2, but the full loop, because it's asking about the electromagnet, and we don't really need this resistor, because it's a different branch. So we're gonna have 12 volts, and that's gonna be lost 2 amps over IR. So we're just going to go 2 amps multiplied by the resistance minus um, minus our we have another 2 ohm resistor, so I don't know the current through that because the current splits at this junction. So minus 2i, and then we also have a back EMF of 9 volts, so that means it's going to be negative 9 volts, and that completes the circuit, and all of this equals 0. So now putting this into my calculator, I get 12 minus 2 bracket 0.09 minus 9. So I get 2.82 minus 2i equals 0, and so 2i equals 2.82, and I equals divided by 2, which is 1.41 amps to be exact. Yeah, sweet. Okay. Oh, okay. Another graph question? Damn. All right. Um, after many more minutes, is the coil steady at 5.72 amps? Okay. So basically, the switch is opened, and we've got a steady current of 5.72 amps. So the first thing we should work out is probably our time constant, which this is just a LR circuit. Yeah, this is a LR circuit. So T is equal to LR. No, L on R. Yes, yes, yes. And our total inductance, 4.5 times 10 minus 1 Henry. Minus 1 Henry. And our total resistance is 20 and 2 ohms, so 22 ohms, which gives me a time constant of 0.0205 seconds, which is nearly the same as the interval one here, as the current falls to 0. So it's going to take the form that your your uh, your current is going to be your current max times e to the negative time constant, right? Your nth time constant, in other words. So after 0 time constants, it's going to be at 5.7224681. So probably going to start somewhere around here. And after 1 time constant, so it's just going to be 5.72 times e to the negative 1, and I get about 2.01, 2.1 ohms, sorry, 2.1 amps, so that would be halfway around there. And then after 2 time constants, I get 0.77 ohms, so that would be around here. And then after 3 time constants, I get 0.28. which would be about here. And then after 4 time constants, I get 0.1. So that's basically here. And then after 5 time constants, I get 0.39, which is very close to the 0 mark. And connecting all of the dots, just assume it's a nice exponential. Alright, just make it up in your head, but oh my god, drawing on this is so hard. Okay, yeah, just assume that that's an actual exponential, nice and smooth. Okay, alright. Explain how the presence of the 20 ohm resistor protects against high voltage sparks. Um, Basically, recall that it's in parallel, right? So when you have two resistors in parallel, it decreases the overall resistance because 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over, like, um, plus 1 over Rn, right? The nth resistor. So it's an inverse relationship. So in basic terms, it just gives the current. It gives the current and alternative low resistance pathway, right? Path. Oh my god. And because the current will split at the junction, so yeah, that's that one. Sweet. Cool. Casey is experimenting with inductors and capacitors now. Okay. Okay. Show that the capacitance of Casey's capacitor is 9.45 times 10 to the minus 7. Okay, so our construction formula is just E naught ERA on D, and that's just going to be 8.9 times 8.85 times 10 to the minus 11, which is the relative permittivity of free space, and our area is 1.2, and all of that divided by 1 times 10 to the minus 4. And putting this all on my calculator gives me 9.4518 times 10 minus 7, which is 9.4518 times 10 minus 7 farads, which is 9 point, that looks like a 9, 9.45 times 10 to the minus 7 farads. Cool. Show to make an inductor, Casey winds several hundred turns of insulated copper wire around an iron rod. And Casey wants to test its inductance. Okay. Casey connects the circuit shown below, and voltage across the lamp is 4.64. So let's just, okay. Um, let's just work out the potential difference in this case. So our potential difference for this component, V equals IR. So our potential difference is 4.64 volts. So your current is going to be 4.64 divided by 5, which is 0.928 amps. And okay, all right. So for this, all right. So we know that VL equals I times the reactance of the inductor. So 11.1 is equal to 0.928 times XL. So XL is equal to 11.1 divided by 0.928, which is 11. 0.96 ohms. Okay. Um, and then what's next? I know XL, so we also know that uh, XL equals omega L, right? Yeah. So yes, we have a frequency. Sweet. So XL equals 2 pi F times your inductance. So your L is just going to be your reactance divided by 2 pi F, which is just going to be 11.96 divided by 2 pi times 50. And putting this all in my calculator, dividing that actually by 100 pi, I just get 0.03807 Henry, and that is which is just basically 3.81 times 10 to the minus 2 Henry. Cool. Sweet as. Nice, that actually worked. Okay. Alright, so Casey adds in the 9.45 times 10 to the minus 7 uh okay. Determine the new impedance. So we know that our impedance is our new total inductor reactance plus our capacitive reactance squared um, plus the total resistance squared. So we have to work out our new XL because we have a frequency now. So new XL is omega L, which is just oh god, okay, which is just going to be 2 pi times. That's just going to be 800 pi omega L, which is 800 pi times 3.81 times 10 minus 2 Henry. 3.81 times 10 minus 2, which I get 95.8 ohms for the XL, and XC is 1 on omega C, which is going to be 1 on 800 pi times your, oh wait, hold on, 9.45 times 10 minus 7. 9.45 times 10 minus 7, and putting that all in my calculator. I get 421 ohms, right? Okay, so also I just realized for this one that actually if you draw a phasor diagram, right, then you will notice that your inductor reactance and your capacitive reactance are 180 degrees out of phase, right? Which means that these two components actually cancel out, and that can also be shown in the equation, right? XL is um, is omega L, or it's proportional to frequency, while XC is proportional to 1 over frequency. So if you increase frequency, you increase your inductance, the reactance of your inductor. However, if you increase frequency, then you decrease your reactive capacitance. So in this case, it's actually just going to be the positive difference between the two. Either way, it's going to be a positive component because it's squared, so it's just going to be our 421 minus 95.8 squared plus whatever the total resistance is, which is just 5 ohms, which 5 squared is just 25, and putting this all in my calculator, So answer minus 95.7557 squared plus 25. I get 325 .33 ohms, which is 325 ohms to three significant figures, and calculate the resonant frequency for the circuit and compare this with the maximum frequency settings of the power supply. Compare. Okay, I should. So I'm not really going to be bothered deriving it. We just know that F naught equals 1 on 2 pi root LC, which is just going to be 1 on 2 pi times the square root. Okay, that's going to be pretty long. What's our L? L is 3.81 times 10 minus 2 into our capacitance 9.45 times 10 minus 7. And putting this all in my calculator. I get 838.77 hertz, which is 839 hertz to three significant figures, and this is 400 hertz. This is more than double. This is more than double the This is more than double than the max F of power supply. Okay. And describe how Casey could physically alter the inductor and capacitor to increase the current through the light bulb using this power supply. So for this one, let's first of all start by writing our capacitor construction formula, which is either you can, so according to this equation, you can either, if you, and we also know that XC is proportional to 1 over C. So if we increase the capacitance, we can effectively decrease the reactance. So to increase the capacitance, I either would have to decrease the distance, so decrease the distance between plates, or if I increase the area, then I could also increase the capacitance, or increase area, capacitor, just say, and we also know that our flux is equal to BA, therefore you could either, for the, and also that EMF is negative N times L times DI by DT. And so if we increase the number of turns, so increase area of coils, or you could increase the number of turns. So yeah, yeah, cool. So that's step one. And yeah, so that's this 2018 2018 electrical systems paper done. I hope it helps. Thanks for watching.